We're starting now to look at the ways of classifying chemical equations. And as it says up here below are abbreviations for classifying chemical equations. We use these with the worksheet balancing equations, which was a homework assignment for last night for the first half of it. And tonight we'll be doing the second half of it. We were only balancing equations. So tonight our homework is going to be using all of these guys that you're seeing over here. Let me kind of highlight it a little bit with the little thing that makes a circle. All of these guys are what we're going to be discussing here in just one moment. But for you to be able to do these properly, you're going to have to understand a couple of things. First of all, a salt is always a metal with a non-metal. And that's something you should put down in your notes now. And by the way, you should stop the recording and copy these down before you go any further. So, salt is a metal with a non-metal. And it is always ionic because that's the definition of ionic. An ionic bond is always formed between a metal and a non-metal. And I think we talked about that before, didn't we?
Yeah.
Yeah? I think so. Okay. And down here, this is a quick, easy definition for acids and bases, which is not really 100% correct, but for our purposes, it's going to serve just fine. So acids have hydrogen ions. Okay, I'm right here. And hydrogen ions are always on the front of the molecule. So if you saw a hydrogen ion like this on the end of a molecule, you wouldn't call that an acid, you'd call it a base if it had an oxygen there. So let's look at some examples, some actual examples of acids and bases, most of which you've memorized by now. But HCl, what's that guy? Anyone?
What?
HCl?
Hydrogen chloride.
No?
Chlorine.
Well, by the way, hydrogen chloride would be a correct name if it were not in water. So that was okay. But what do we call it when it's in water? Hydrochloric acid. Good. Do we have anyone who knows what this is?
H2SO4.
Yes, it's H2. Yeah, what did I hear? No. Believe it or not, hydrosulfuric acid is this. H2S.
Really?
Uh-huh. That's hydrosulfuric acid. It wasn't a bogus name, it was just not for this molecule. Okay? So what is it for this molecule? You're kind of in the right ballpark so far as the name's concerned. It's sulfuric. Sulfuric acid. And what's our dude over here? Who's he? Who's this guy? H3PO4. Phosphoric acid. Good. Okay, this of course we'd call sodium hydroxide, calcium hydroxide, and what do you think? No, not oxide. Hydroxide.
Aluminum
Yeah.
hydroxide.
Yes. So, what we have here, you'll notice that the OH is on the end of that molecule. So one more time, hydrochloric acid, sulfuric acid, phosphoric acid. And here where you see the hydroxides on the end of the molecule, that's what we're saying up here, right? Okay, bases have hydroxide ions on the end. And so even with water, you can see hydroxide on the end, although this is not a base. Sometimes we write water so it looks sort of like a base. And so the reason I showed this equation here is when we're doing our classifications, sometimes it's especially when we're doing balancing equations, sometimes it's very handy to have water as H2O broken down as HOH, so that you see that this hydroxide is with the hydrogen, and that hydroxide could be with someone else. So that's the purpose of having that there. Now, in this slide, now you're going to see over here in this area, I have put down exactly what you're going to do on your little sheet for balancing equations that you did last night. So I've got two classifications here. One of them is not explained on this page. So let's look at synthesis first, and you notice I circled synthesis SYN here because this formula was originally used to talk about synthesis, which is A plus B. Okay, so A plus B becoming C. Synthesis, you're putting two things together. And the two things we're putting together are the sodium and chlorine. And are these ions or are they elements?
Elements.
They're elements. Okay, they haven't become ions. Yes, Destiny?
Why does the O2 on the first half of the magnesium plus oxygen, why does the 2 disappear on the other side?
The 2 disappears on the other side because what is our charge on magnesium? See where he is? Magnesium's number 12. What's his charge going to be? I'm talking to Destiny now. What? What column is he in? Okay, everybody in the second column is a 2 plus. Okay, do you know what what about oxygen? Oxygen is element number 8. What column is he in? What column number is that? Yes, good, 16. So everybody in 16 is 2 away from a noble gas. And so they gain 2 electrons and they become 2 negative. All right, so magnesium is 2 plus and oxygen is 1 minus, or 2 minus. So you just need one of each in that molecule. So putting this 2 over here would put it out of balance. And that's the reason why. It was a good question. So when I drop magnesium into water, sometimes if the magnesium is clean enough, you'll actually see a bubbling going on. And there's going to be fun stuff going on.
Is magnesium the thing you turned on and it was like that bright light?
Yes, that's the bright light that we did over in the sink. Yes, it is. And this guy is not in water. He's just the magnesium itself, the metal. And then when we put the torch to it, he actually burned, and that burning is called combustion. And it's combustion because it combines with oxygen. But it was just another example of a synthesis reaction, just like this guy is. But you notice I said here that this is also oxidation reduction. And so oxidation reduction means that these guys starting out over here have no charge. So let's look at that. Sodium is no charge. Chlorine is no charge. But over on the right side of the equation, where you see sodium here, what's his charge? 1 plus. Yeah, this guy's a 1 plus, and this guy is a 1 minus. And the ox red that I've got over there, and let's go ahead and point to it for the video purposes, this ox red is simply saying that the oxidation reduction is that somebody's starting out as an element and it's winding up as an ion, or it could be the other way around. 2 ions come together to form an are broken apart to form an element. And that is the reverse of this water reaction down here, the way we make water, or one way to make water. So we've done the synthesis. Let's go down and look at combustion. So I'm doing combustion here. I called this a combustion reaction, but he is also classified in 2 other ways, as synthesis. Okay, the synthesis is the first one we talked about. So this guy could be used as synthesis. It could also be used as oxidation reduction, and it is a combustion reaction. Now, why is it a combustion reaction? Because of this guy right here. Okay, if these guys come together, that means that we have combustion, but it requires oxygen. These 2 came together, but there was no oxygen. Okay, so right here we wind up with water, and because there is oxygen involved, both in this one and in this one, that classification becomes a combustion, C-O-M-B, or C-O-M. Oh, I shouldn't have put the B there. Let's take that off. I just used C-O-M. C-O-M for combustion, that makes it less to write. Okay, so let's get that fixed up back here. Ooh, red and green together, huh?
Yeah, Christmas.
Yeah, right, just like Christmas, of course. So, are we clear here on combustion? We've got oxygen involved. That's what has to be here. Okay, so you see it up here, you see it here, and you see it in this particular example. So, why is it that this equation, the first one that I showed for synthesis, why is it that this guy is not oxidation? I'm sorry, why is it not combustion? Why is this equation not combustion? Anybody? What does it need to be able to be combustion? Oxygen. Okay? Yes, the oxygen. This guy right here. Okay? The H2, or the O2, makes it a combustion reaction. That's the only reason we call it combustion. And what's a common combustion reaction that you would see if you were out in the forest and all of a sudden there was a forest fire? What would the combustion be?
Fire.
Oxygen with what?
Wood.
Wood. Yes, wood. Just that simple.
Wood an element?
Wood is a compound.
Of what?
Yeah, mostly cellulose. Cellulose is carbon, hydrogen, and oxygen in a specific combination. Yeah. Okay, so let's move on. We've got the oxide. I hope you're all writing this whole stuff down. Everything is supposed to be written down. And if you didn't write it down, you'll have to watch the video tonight. Anyway, two become one. That's the deal here for synthesis. In the combustion, we also had two becoming one, which is why it can also be called oxidation reduction. And then synthesis, because, two become one. That's why it's a synthesis, oxidation reduction, because we have oxygen involved in the reactant side. Notice here, notice what that says? Right here, just say, let me get this so it doesn't keep flapping up on me here. Okay, right here, this guy, right here, oxygen must be on the reactant side, or the left side of the equation. If you have oxygen all by itself over here, it's not oxidation reduction. It has to be oxygen as a reactant. Okay? Let's go on, and let's get a pointer back here. So the two that we're going to deal with on this page are decomposition and single replacement. So decomposition was A being pulled apart to make B and C. So I rewrote that here. A is being pulled apart to make B and C. So here's our A. What's the name of this ion? What is this ion?
Nitrogen. Nitrate.
No, it has a name. Ammonium. This is the ammonium ion, NH4. Okay, I hope you're writing this down. Nitrate, over here. I was going to ask you. I blew it. Okay, anyway, this is nitrate, NO3. What's the charge on nitrate?
3.
No, that's 3 oxygens in the nitrate ion. 1 minus. 1 minus. Okay, so what's the charge on ammonium?
1.
It's your only positive polyatomic ion. The only
one is.
The only positive one is ammonium.
And the rest are
All the rest of the guys are negative, 1, 2, or 3.
Oh, I see.
Yeah, okay?
Oh,
So, as we go over to the other side, you'll notice the 2 nitrogens here wind up in the dinitrogen oxide and the dihydrogen oxide, also known as water. Okay, so this is decomposition because this guy gets pulled apart. We don't see nitrate on this side of the equation. We don't see ammonium on this side of the equation. They have been totally disassembled. Okay? So this is decomposition. And that is the only classification I could think of to put that in right now. All right, here we have, if we look back up here, we have the AB plus C going to C replacing B to become, or C replacing A to become CB. and then A winds up getting bumped and winds up by himself. Right? So this is our single replacement dude. So here we have, you see, here's my AB, and here's my C. The hydrogen here, and if we look at it again in the sense of, let's get this guy out of the way. And there we go, extend the page, and I don't have to worry about this guy bumping on me again. And now we come back up here. So with hydrogen here, instead of put into a situation that makes it look like this, we have actually hydrogen on either side. Brian, before you get sentences, move back. Go. And so the hydroxide part goes over here, and the hydrogen that was here is being moved over to here to become an element. So he's a 1+ here, and he has no charge here because it's just the element. Okay, here he was an ion, so to speak. Now the lithium was an element here, and here he is an ion. So he was a 0 charge here and a 1+ charge here. So this guy has replaced the hydrogen in HOH, otherwise known as water. And when the hydrogen gets bumped, he becomes a gas and becomes H2, the element with no charge at all. So this is two kinds of equation. Single replacement because the water or the hydrogen here gets bumped by lithium, and it's oxidation reduction because there's a change in charge, like I explained earlier. And let's look at another ox redox. This guy is water, where calcium now is replacing hydrogen. And so we get calcium hydroxide. And if we put litmus paper into the water where this happens, it's going to be basic. And we're going to see bubbles. And you already saw this.
Oh yeah, in our lab.
That's right. We had little chunks of calcium, remember? Little tiny guys like that.
We dropped them in the water.
Dropped them in the water, and you saw a lot of heat, right?
Getting my base.
Oxidation reduction is always hot. Okay, oxidation reduction, always hot. How? Hot reaction. Okay, it's always a hot reaction.
Always
Thank you. Always hot reaction. And let's make that a red so it looks hot. See, it looks so hot. Isn't that great? Okay. And let's go ahead and make him a little bit bigger. Always a hot reaction. Now I should put some flames up above that, right? Okay. So this is our oxidation reduction. It's also single replacement. Now we have a couple more here, and then we're done. And we've got a first of all a double replacement. The double replacement is where we have two guys together here and two guys together here, and they switch partners. See what happens over here? A is with B on this side. Now A is with D on the other side. And here is C with D. Now C is with B.
Why?
Because it's that kind of reaction. That's what happens in those kinds of reactions. This side has less energy than this side. Not by a lot, but it does this because actually this one is driven by the formation of water. So what's going on? Calcium is getting left behind to form calcium chloride. Now this is not calcium the metal. Okay, and this reaction is going on in water, by the way. So the calcium now becomes calcium, or gets together with the chlorine as calcium chloride, and it won't be that way until we get rid of all the water. When all the water's gone, it evaporated, and this guy's all left alone, the calcium ion will grab on to the chloride ions, and that's what you will have on the bottom of the container when the water evaporates.
Like the salt.
Like it is a salt. A salt, remember the definition that you had before? A salt is a metal and a nonmetal.
Salt is a metal.
Metal with a nonmetal.
What do you mean?
Calcium is a metal. Chloride is a nonmetal.
Oh.
And they are together here as an ionic compound. Yes, Meher?
Why does water evaporate?
Water evaporates because of the heat that is going to be generated, or the heat that's going to be taken in to do that. It requires heat or it won't evaporate. And so if you get water below freezing point, it's not going to evaporate. All liquids will evaporate to a degree. But the only difference is how much temperature it has to be to make it happen. Okay? So let's finish this off. Here is a double replacement. It's also an acid base. Who can tell me why this is acid base?
The right way. Because of the
Okay, what's the base? How do you recognize the base?
O2. OH.
Good. You got it, James. Okay, the OH here is tagged onto the end. Yes, that makes it a base. And how do we recognize the acid?
H.
Yeah, the H is in front. Okay, here the H is in front. So that's the acid, that's the base. Now, here we have a salt and water. If you'll look back at your notes from earlier, you see that you have a salt plus water is being made as a reaction, or as the products of an acid-base reaction. You always get salt and water. Not always sodium chloride salt, but you always get salt and water. And so, yes, calcium chloride is a salt. All right, so we've got acid-base and a double replacement. Now, the primary thing that I was showing the second equation for was to get you the oxidation reduction. And that's why I have oxidation reduction, ox-red is circled here. So for this guy, sodium is a metal, chlorine is an element, the elemental chlorine, and when those two guys come together in a flask, usually this is you have to get the chlorine gas in a flask of some sort, like an Erlenmeyer flask, and I have an actual video of these two guys reacting, and it is so hot and there's so much light given off by this reaction, it's kind of like magnesium burning. Okay, and it just whites out the screen almost. And so you know that this is a hot reaction, and oxidation reduction, just like we said in the last one here, oxidation reduction is always hot. Okay, so we got oxidation reduction again, and it's a hot reaction, and this is also a synthesis reaction because two become one. Okay? Yes, sodium and chloride. Chlorine over here, chloride over here. Uh-huh. Yes, exactly the same. And so there you have the explanation, and here you see sodium is a 0, chlorine is a 0 charge, and over here sodium ion is a 1+, and chloride ion is a 1+. And now you know how to do classifying of equations.